And we switch to the panel discussion.
That's a shit here.
Yeah, it's mine. I can sit here.
I think we need to put the chairs.
But the thing is, the microphone, they can't be
I see.
used over there,
Okay.
so they have to sit around the table.
Oh, it's a wire.
Yeah, that wire. Yeah.
Okay.
Thank you all very much for staying until the last event of the day, which is the panel discussion with our. I think that the panel is going to be interactive. So we'd like to one of you to start your background over here. And if you don't have any functionality, you can just go to slido.com. There's going to be 3 topics, and for each topic, you can the question related to it. And you can also upvote the question that you like. And I try to ask the question to the panel, the question which are the most popular. So maybe let's begin by introducing the panelists with a brief bio. So Andre is the Deputy Scientific Director at Valeo AI and Research Associate at the Astra Inra team working on perception for assisted and autonomous driving. Alex is the co-founder and CEO of Wave. He founded the company in 2017 with the belief that end-to-end AI would unlock generalized autonomy at global scale. Hong Yang is an assistant professor at the Uni of Hong Kong and research scientist at OpenDrive Lab. His research focus is on autonomous driving and embodied AI. Christos is a lecturer and senior postdoc at ETH Zurich. The focus of his research is on semantic and geometric visual perception. And finally, Ted is a senior researcher, research scientist on the robotics team at Google DeepMind, and he works on problems in scaling robot learning, foundation models, and reinforcement learning. Let's begin with the first topic, which is around the technical challenges around building a foundation model, where we're going to talk about data, model, and algorithms, all the good stuff. So let me begin with this first question. One of the assumptions under training a foundation model is that we need to find the recipe, which includes a model architecture, training task, data, and so on, which is computationally efficient and scales well with data and model size. Do you think as a research community, we have converged on the recipe? And how do you ensure that the training task leads to a representation which is general enough and usable for downstream tasks? So who would like to get started on this question?
Given that my talk was on the missing pieces, I would say no, we do not have the solved recipe yet. I think we have very great existence proofs and signs of life that we can get to this recipe within the next maybe year or 2 or 3. But I think we do not have all the missing pieces ready today for either the data problem or the algorithmic modeling problem.
An interesting comment I'd make is that I think we need to go all in on diversity. What I mean by that is, we've seen in the language community that if you train on a data set that is, say, predominantly one task, let's say comprehension, and then you have a little bit of data of something like mathematics, it won't perform very well in mathematics. But if you have lots of diverse data, comprehension, reading, I don't know, like I'm not a language person, so I don't know the different tasks. But if you have like 100 different tasks, very diverse and balanced data sets, then you learn these general purpose programs to tasks like mathematics. And so I think I take from this is that if we really want to build a foundation model which is truly embodiment agnostic, what I mean by that is that it can be deployed on a new robot and not, and understand what that sensor setup can or can't see, understand how that system can operate in a zero or few shot setting. I think we need to go all in on diversity of data platforms at scale, and I think that's something I'd love to see more of. I think there's a huge gap between the data sets we're seeing in mass today and what it's going to take to make such a foundation model possible.
Thank you, Ted and Alex. I have a question from the audience, unless you want to add something on the topic.
It resonates with Alex. You gave a response which was pretty generic, so just to put things down in perception, for instance, which you're also doing it at Wave, why is it important, this diversity? Because I was also tracing on that we have driving data, but it's not sufficient. I mean, you still need the internet, the homemade, all these videos to catch all those corner cases that you will never see in driving. And in addition to driving, the thing that crossed my mind recently, seeing this paper Dora, I don't know if you saw it, where they do self-supervised retraining on walking tours videos. So they take videos from YouTube, like 40 minutes to 1 hour, and they do a pretty self-supervised retraining just on one of them. So it kind of made me think also what you guys are doing at Wave, driving a car, and I remember your early days with the Twizy. Why not? I mean, adding to this spot, I mean, the pedestrian perspective, right? How does the pedestrian see the road and interacts with it? How does the biker see the road and interacts with it? So it kind of, I think that bringing to this, well, you can not only check it by giving it feedback, but also having the raw data of acquiring some diverse data, visual data to in your environment that your vehicle or your robot will interact with. I think it's quite important, and there's cheap ways of doing that. Of course, we like having them calibrated with LiDAR, with all these things, but we saw with some colleagues, with the colleagues at OpenTrack, that with this open TV tablet, you can do quite a lot of things by exploiting some existing data sets on the side for the engines.
Thank you, Andre. So for the panel question, I'm just going to be democratic there and ask the question which are the most upvoted. Starting with this one with 7 thumbs up, which is a bit spicy actually. So, question is autonomous driving really the best path towards embodied AI? It seems the embodiment is simple and focuses on navigation, minimizing environment interaction. Who would like to take this one?
Okay, well, I wrote a blog on this recently, so please have a read if you want to dive deeper on Wave's websites. But look, it's interesting. If you look at the results from RTX and you look at navigation and manipulation data, navigation data improves manipulation more than manipulation data improves navigation. That's a really interesting result. It suggests why this is. I was actually debating this over lunch with some colleagues. Well, why might this be? I don't have any data, but a hypothesis might be that navigation is, tends to be more varied in the visual scene and the dynamic nature of the data, the open set world that we might drive in, compared to, say, manipulation or manufacturing robotics, which tends to be more of a closed and controlled ecosystem. But that's one example where I really believe the point that autonomous driving is the most economically viable and possible path to scale data in an open setting. And I think that is what is required to build and enable a foundation model for embodied AI. So for that reason, I can't see if, just to look at the counterfactuals, if you look at humanoid robotics, I think humanoid robotics is really like self-driving in 2017, right? There is a very expensive hardware path ahead of us to build platforms, and they're operating in very constrained environments that are a bit like Phoenix and Arizona, like where self-driving started. or manipulation robotics and manufacturing tends to be in very constrained, repetitive tasks. If we really want to build embodied AI, we can't have these constrained and simplified environments. We've got to be exposed to a problem at scale, and I think there's no better opportunity for that than self-driving. My prediction is I think self-driving will enable us to build the first foundation model in a way that we really solve the safety and trust problem. And then we'll be able to take that and generalize it to those other domains in a way that helps them as well. But I don't see another robotics domain that is getting access to as much open set and diverse data as self-driving. And so, when we started Wave in 2017, we wanted to build embodied AI. Actually, we were debating this, and the reason why we went into self-driving is for this reason, because it's economically viable, and there is the hardware out there today. There are vehicles literally being shipped in production lines at millions of volume that have surround cameras and an onboard GPU that make it all possible. And so I think it provides a path of least resistance to embodied AI at scale.
I tried to argue a bit against. So I think we need to take advantage of every person's routine in everyday life. And we have, of course, driving as a core part of our routine worldwide. But we also have, for example, cooking, where we can have also current advances in AR, VR, and mixed reality. We can have also massive data of real experts, people, in everyday indoor activities. Of course, the hardware that we need to basically simulate or construct is not as advanced as you argued. Indeed, for cars, cars are really robots, if you think about it, that are there for 150 years now. But if we can have access to a huge amount of data also for this different setting, and with this we can hopefully also build better models for embodied AI. So I think that, of course, I'm more on the driving side, so maybe talking against myself here, but I think that there are definitely also other alternatives that have certain pros, and perhaps navigation is one part, because you hope that you don't even touch the other agents, you don't collide with them. But manipulation is even more challenging, because you have also this more intricate physics, grasping and finding the correct pose, exactly reasoning about very detailed geometric attributes. So there we can also have more challenging tasks to solve.
Thank you very much, both of you. So moving on to the next question from Dipti, which is: to achieve robust/generalized model, should we focus on obtaining diverse data or on learning techniques for robustness, like those in domain generalization literature?
Okay, the question is, do we need to learn more data?
Yeah, so the question is about how to build a truly general model. Should we focus on the data part or on the algorithm part?
I would definitely go for the data part. So I will narrow down this question into a technical, or this is an academic conference, right? It's not an expo or whatever thing. So everyone is talking about foundation model. As I mentioned earlier in the morning, there is not a single definition exact definition as to what is a foundation model specific to be specific in auto-driving. The only two papers that I've ever seen on arXiv, not to mention is accepted or not, as for the foundation model for auto-driving, one is the Gaia paper, and the other one is a JNAD paper. So the other papers are all discussing word models or foundation models, or how to fine-tune the VLMs into auto-driving on new things, which is only 5 hours of data, and which consists of 90% of the things are simply going straight. So this is insane. So this is the reason I barely see papers nowadays. So I will definitely go for the data part, but to put it into real implementation, we really need to have some collaboration to prove, okay, so for the VLMs or LMs, they have proved so the effect of scaling law are to have massive amounts of data, and you can show great capability to achieve generalization. But for auto-driving or for the embodied AI, or I would use rather prefer robotics, the term robotics. I've often heard some people, some professors from Jiajun or other professors, even in robotics, they don't have massive amount of data. So that's why they have this concept called data pyramid. So compared to the general vision, where you can easily get web data, billions of data, we really should get some collaboration mechanism to collect all the data whenever you try in or robotics, and try at least to try the scaling law in auto driving. So you know what? So the GenAD data set you mentioned, as Chenny mentioned, it consists of 3 T of storage of drive. If you have the storage is 3 T, and you can imagine since I'm a little bit lengthy, I'm sorry about that. So since it's released, I think it has been released for 3 months or 4 months. I think there are only a few downloads. So in the academia, so really few people can have the storage or have enough GPUs to train or to even testify the generalization capability. So in my sense, since I'm from the Shanghai AI Lab, it's kind of a hybrid between the university, which is very poor in its resource, but it got brilliant ideas, and between the big techs, it's got great power or resources, but it got pressure in the production, so that it has few space. So I would rather encourage people to contribute more in the data exploration part. I'm not sure I'm making it very clear, but that's the sense.
Just because I agree with you. I just would like maybe to nuance a bit. Because yeah, we've seen that the more data, the better data, the simpler tend to be the algorithms. But yeah, when you're constrained in resources, or if you think of a short-term horizon, I think algorithms is related. And kind of speaking also from your standpoint, maybe to resonating with what you said, Alex, you also want an economically feasible solution. So speaking from with the hat of an ADAS guy, we need to deliver things for the ADAS for the cars right now. Well, you want to finance what you'll do in 3-4 years from now, where data will take over. So now the algorithms kind of may have a bigger role. Then, assuming that you have all the data that you want, you still have an algorithm component related to the data itself, to the curation of the data itself, and the filtering. Take V2. Well, algorithmically, there's nothing new, but the big contribution there is the cleaning up of the data that they did at a web scale, finding automatically what data is relevant for your self-supervised test. And actually, some of the guys left and created a startup for data curation called Dapology. So they said they run a business on that, and it's something useful. Also in LLMs, it's kind of the same thing. The amount of effort that is invested in there, certainly you have the scaling laws, but before you get to reach your data set, there's some certain amount of cleaning that you need to do. And speaking of the long tail of events, because that's what we care of, well, they're long tail, they're rare, so they tend to be dominated by the main modes, but also there are many long tails actually. Right? We call it one event that is long tail, but actually there's a more of them. So they're not selected properly, addressed properly. They can either become nodes, or they can just be faded out in the lab. So there's actually quite a lot of algorithms and know-how to be built into the data itself, such that then you'll have your life easier with very simple algorithms that can just leverage whatever you have in the data and have your very nice one.
Yeah, I think one of the interesting things we often debate around is, if we took our current stack and scaled data to infinity, would it just solve self-driving? And I think the answer is unclear. Like scale of data is certainly necessary. And to be able to build these kind of systems into a product, you do need call it a scale of data to bring these systems out. But is it sufficient? I think the distinction I draw when it comes to working on algorithms is that we should strive, and as a team we often talk about this, is that we should work on algorithmic improvements that will survive the test of data. So what I mean by that is finicky little augmentations to solve things in a low data regime. I think they will be solved by data. If you think about as data does scale, and particularly if you're fortunate enough to be in a position where you are growing it by 10 or 100x year on year, like what we've experienced at Wave, then what are the algorithmic challenges that will survive the test of that? Can you build a representation that's aware of something, aware of what it's can or can't see? Can you build a system that increases the temporal context window or something like that? All of these are examples of what we can realize that examples of things that survive this.
Thank you very much to all of you for your answers. Moving on to the next question, which is from Anonymous. How will the chicken egg problem of data scaling for robotics be solved? No deployment till they are good enough, which requires large scale data.
I've I don't know if this will be true or not, but there's a belief right now, at least in Silicon Valley, I don't know how many years I'm from the Bay Area, but that the bootstrapping problem of the chicken or the egg is something that just can be handled by VC checks of a cumulative of like $30 billion. Like you can just get past this problem by just running like paid data collection operations either locally in warehouses or out at paid customer sites, and you can just get enough data, I don't know, million trajectories, 10 million, 100 million trajectories, and just bite the bullet, pay that upfront cost, and then, maybe after that, you solve the chicken and egg problem. I don't know whether this is true or not, but it's being explored right now by probably like 3 other companies in Silicon Valley and around the world. And I think we'll maybe get the answer to whether this approach will work in like 5 years. But yeah, just one data point at least.
I think we're going to find the best way. Brute forcing it, I think there's going to be the best way. Robust to be honest, there are those customers out there where we can and being so required to follow product. One example is driver assistance. Driver assistance allows you to put a system out there where it fully robust and it's something you can learn with development and application, but others get it growing. Examples that can allow us to grow out. I think that's what we've found a way to being out AI to deploy as a driver assistance stack, and the extension to that will allow us to scale data to train and validate a system that can be deployed as an L5 or L4 authority system. But I'm sure there are many others out there. That's perhaps a different way of relying on our capabilities.
So I think also there's nothing about simulation, right? Whether we can actually bring humans into our simulation in creative ways, so that, for example, for mapping, there was this Pokemon that they basically gamify the reconstruction or the mapping of that very difficult parts of the cities. Regions. So if we can also efficiently put humans in the loop, I don't have a clear this might be easy, but I think we can also try to make our systems more business.
So maybe one last question on this topic, and we need to move on to topic number 2. The last question is, what role do you see for sensitive data coming from traditional simulators?
simulations. For example.
Yeah.
So it's not real. So you will be faced being asked all the time. So what's the real question? So that's why I've seen some advertisement from some companies saying that their performance or their effect is more good. It's more realistic than the color, but it's still really demo level. So it's really a big challenge. So the very key techniques behind all the simulations is how to use neural rendering or the Gaussian splatting, especially with the turbulence or the other forces or challenges, especially facing different scenarios or cases. For example, the part moving downhill or going to situations or facing traffic installations. So it's really challenging, even for the neural rendering community itself. So if it done it right, you will have this universe in the engine create a lot of safety critical cases. So I would bet that simulation is a very good platform or a very scientific we will no offense, color has its historical role to provide a very fair valuation platform, but the community really need a way better simulation engine.
So I think there are two main aspects here. One is the rendering quality and the realism of the visual appearance, and this has to do with reflectance properties, geometry, materials, and I think that in this regard we need to look more on the computer vision community graphics community materials. So we are much more progressive in terms of geometry, but I think we need to look more there because there are not really, again from the data side, not really very good real world data sets especially for outdoor scenarios that model materials, and this can be really important where we have different conditions, for example, wet road with very intense specular reflections and other medium density, medium density, etc. The other side is about the behavior realism. So this is more on the, let's say, prediction, world models, and I think there, the traditional simulators, they have some very nice heuristics, but probably with more advanced and hierarchical and compositional world models, it can bring it to the next level. But I think it's still a very valid baseline.
My friend, I think you could because so the learning is really hard and really versions languages from here. Well, of course, we had NERC and the other units from Wabia. Just let's see if there were several by either. So already we've seen, because of the particle framework that you have in Gaussian flatting, you have more and more people that are excited by the physics. I don't know if you saw these Gaussians, and there's a few other papers like that where they insert the physics and they start deforming the objects and introducing the physics there. And if you couple with what we saw in Prism 1, but also in others, rendering simulators, environments that we have there, we'll revisit the notion of simulation, I think, based on that. Because once you have access to actually having an impact on the object and getting the feedback, because there's some physical realism in terms of training, but also validation, we can go pretty far with these types of new generation simulations.
Thank you, Andre and Christos. So moving on to topic number 2, which is about real-world challenges in embodied AI.
let me begin with this first question. Let's assume we have trained a foundation model. It was trained on a wide variety of data in a big compute cluster. It shows superhuman performance across a broad set of tasks, ranging from perception, prediction, planning, and reasoning, the dream. What are the unique challenges in leveraging this foundation model and specialize it to a particular task and embodiment? Would like to get started on this one.
Speaking at least right now for manipulation, one of the open challenges right now, again, is how exactly do you fit a broad generalist foundation model into an embodiment while retaining the generalization, the intelligence, the constant transfer that you get from the base model. I think this right now, at least, is very understudied because the data distributions of your in-domain robot data is just so far from the pre-training pictures that these large foundation models are trained with. And so I think until we can figure out either an algorithm that makes bridging these very these data islands that are sparse together, or you can actually just fill out the data islands with some kind of data that is friendlier towards your model, so to speak. I think until we solve that gap, then fine-tuning for a specific robot embodiment you're gonna lose a lot of the reasons why you wanted to start with foundation models to start with.
I love talking about engineering. So getting the algorithm right is just a start. I think getting these systems integrated into a robot platform is an enormous task in itself. Optimizing inference, drivers, all of this kind of stuff together, and making that all work seamlessly is an enormous challenge. Building the right safety case allows for fail-safe or fail-redundant pathways, ensures that you have a some kind of whatever your model of safety is in play that allows you to quantifiably measure performance. All of these kind of tasks are really critical. Underappreciated when we talk about getting a system built, but to go from a demo that's we've all done this at a robot demo where it's sort of duct tape and handheld, and it started from command line into a slick product that can be operated with a UI that doesn't require expert training to use, and actually just works not just 99 but 99.59% of the time. This is really what it's going to take to make these kind of systems scale, and something that we've been a lot about recently. I like when it comes to inference, I like the opportunity that integrated systems propose. Because there are such great libraries available today for optimizing systems, because it's relatively accessible as opposed to robot systems of the old that we we build one ROS and a really nice message passing system. We've got so many different nodes that run asynchronously that need to pass with different latencies that pass messages around. The nice thing about an end-to-end stack is it's just one neural network, and you're simplifying this, but your inference node is just modeled up forward. Is the option here.
Also about finding the module that you can keep intact from your pre-foundation model and not touch at all, and finding also the other modules that you might want to adapt to fine-tune where that relates to the task. And also, I think you might need to design that you want to talk to Andre before, like what tasks you need to solve in each case and how you choose these tasks. Of course, like we have heard today that you can try to unify this task together and try to blur the boundary between them, but sometimes you have to make some decision, like what your output will be, and then you need to also find to define the scope of your application, right? What is the target domain, the operational design domain that you want to address? So this can change a lot all these other points of alignment.
Thank you, Christos. It's actually quite hard to find questions because you're answering questions as they come. So you have to find a question which has not been answered before. And I think I got one. Is there a gap between what students learn at uni and what's required to solve real-world AI problems?
I think many of us are trying to close this gap as much as possible. So trying to stay up to date with the latest developments. Of course, you need time to also integrate, as an academic teacher, these parts and still provide them in let's say, didactic fashion. But I think that we're trying our best to also provide the resources from the university as much as possible to students so that they can solve real-world, state-of-the-art, cutting-edge tasks. And I think this has also great impact to attracting researchers afterwards, after they finish their studies, both in the academia and the industry, to keep working on these problems and not just change gears or go to more mundane, real, low level applied areas.
The question was for undergrads, for high schools, and PhD students.
Undergrad. What's the question?
Okay, good. Well, in a previous life, I was quite involved in engineering education at the European level as a student, so we had the same question. Yeah, how relevant is what engineering students are studying to the market, because there was internet. There was always something. So personally, I'm more optimistic because as time advances and of course the bar is higher, right? It's higher than ever for any job, for anything right now. It's higher than ever. But also, I think at our reach, we have students, but also us included, because I think we're continuing to be students ourselves in various aspects of life. And technical is that you have so many resources and so many things you can access to. What I think is one of the most important things is to keep your curiosity alive, whatever the means you can do. Because that's what's the most important thing. Well, you will never, as an engineer, it was the case before, and it's definitely the case even now. It does not end at the end of your school. You're always learning, you're always advancing. So, and I think that will not change. Maybe the rate can seem more accelerated, but I'm not sure about that. So you have some meta patterns that are there and that you can grasp on. And I think we have a lot of the needs and so many content that is free, archive, code, Cola. I mean, there's a lot of things that are reachable for many of the students, provided that they're able to see the
The curiosity is such an amazing good. Specifically, some of the things that I found really helpful in my experience going through. I've also agree that we're still students, we're still learning, we should be, but I found that outside of the technical research skills, well, some of the things that were really important there was knowing what not to work on as well as what to work on. And
Never release that post.
skill research ideas, making sure you have a portfolio of things in the funnel was really important.
Give me some video
during
demos.
my PhD. Giving talks was a great way for me to actually stress test my ideas, but it forced me to put together a narrative. And I found that going out, putting yourself out there to give talks was a great way to learn and to refine your ideas, as well as learning to market and sell your ideas, which is a big part of growing, your research base as a researcher, or even growing collaborations and things like that. And then outside of that, I think the complementary skills that I was fortunate enough to do an internship at the most incredible robotics company, Stadio, during my PhD. But that taught me skills from even just coding in a team to building unit tests. And I came back in my PhD repo and immediately flooded it with unit tests, and it just made it like a lot better. Anyway, these kind of things to source control, actually doing that properly, Whereas before then, I just didn't bother with my demo code, and again, it was a nightmare. And so all of these kind of skills about how to software engineer, I could recommend highly enough. But those things are work for me.
Thank you, Alex. Moving on to the last topic of the day, which is about large-scale deployment of those autonomous systems, especially in safety-critical scenarios. So let me begin with this first question. Given that embodied AI operates in the real world, we have a responsibility in terms of safety when deploying our AI models. According to you, how are foundation models better placed to solve the long tail of scenarios? Those extremely rare scenarios that we oftentimes only see once in a lifetime, but that we need to perfectly handle. Yeah, but are pretty good to perfectly handle.
That's a challenge that I haven't figured out yet. But I think if you make an analogy to humans, right, we can't imagine. We've seen several really dangerous stuff, and we just made media reactions to those cases. So if the large language model, the so-called language model, has some capabilities of knowledge, then the key part is how to transfer those knowledge into the autonomous cases or to specific autonomous applications. So then again, we are back into the problem. Our data cannot create the basics or whatever we have seen. So this is why we need simulation or simulation intelligence or whatever. So so my guess is we can bundle with this problem with the new benchmark or data engine to create some cases and see what.
One interesting perspective I've been thinking about, and we haven't touched on this earlier, but is that I feel like actually the progress towards the deployment of autonomous systems that will count with humans at a society scale, right? You have like, large scale autonomous vehicles. And again, these are also very safety critical systems. But then you might also have deployments of home robots or, with factory settings or humanoids or whatever, that will maybe not be safety critical, but also will have a large kind of compact space where humans and, the elderly and children and then your pets will be interacting with them. Even if it's not safety critical, it's not life or death. Those are very different types of human-robot interaction than you see when, a human and a self-driving car are interacting in the road, right? So I think it's also interesting to think about whether or not the behavioral prediction problems in self-driving also transfer to HRI within a home or within a, like a retail space, or whether these are different problems altogether. Thank you, Tim. Yeah, that's it.
So it's interesting because also with technologies that are not strictly speaking AI, like cell phones, we see that the whole social behavior of human beings changes. So you can see like all of us are now with the cell phone all the time, and this also creates more, let's say, not on the, let's say, pure physical side, but also on the emotional, mental side, different like patterns, problems, but also new opportunities. So we need to stay close and grounded to the end users, and for this we also need to really pinpoint to them and to the community the limitations, and not be shy or afraid to show the failure cases. Actually, this can be even better because with the failure cases we have like the loss or the training signal in order to improve and then iterate on the method space and make more advanced and more reliable, more ethics
linear models. Very rough, I'm speaking very rough, of course, it's huge, like, components.
Thank you, Christos. And here's the last questions, and we're going to stop torturing the panel. So, final question is, how can we build public trust in deploying learned systems in the real world, considering the potential harm caused by embodied AI? That's one.
Yeah, I think this answer is setting these expectations with society, and so everything from the way that the market would communicate or talk about these systems, as at the point, actually, you know, in the UK, self-driving cars just got legalized through Parliament, and one of the key things in this law was not only the safety requirements in these systems, but also marketing language to ensure that the correct expectations are going to be set with consumers. So that's one point. And then of course there's ensuring that we build them not just with you know, performance of market, give them a sense of what those boundaries are, and then the ability to detect distribution or things that go beyond what we can quantitatively that we can operate in, and then building backup mechanisms or things like that to be able to support it. So I think these kind of things are important. You can also talk about it from an experience perspective, like in a self-driving car system, you know, building up exposure to it through, say, driver assistance, or if there's a robotaxi or ride-hailing service, maybe mixing it with you know, other vehicles that human-driven that aren't limited by snowstorm or stuff like that. It keeps the experience more seamless. And then as the systems get better and they can start to produce a more effective deployment, will start to grow them. But I think about that gradual increase with setting the right expectations is what generally builds trust over time. That's one way to think about it.
Probably we used to call autopilot something just right on the highway. If it was speed constant, you'll have a hard time but the ultimate three functionalities that you'll have. Would feel like a retail fallback from whatever model is the autopilot, you know, release. I think, and I relate so much, I didn't know this part of setting expectation. It was great that you but I think that we need to make right, and it's which is really tough. And I think that you touched a bit on that, is really the evaluation, how to properly do the evaluation. And there's a lot of work to be done there. You take doctors. Doctors make mistakes, but usually you have to become a doctor. You have an exam, kind of everybody knows that this exam is a clear assessment of the competences of that person. Of course, in time they will get better, but it's kind of enough to have them after all this training, these years of training. You have these exams like for lawyers and so forth. You have some way of certifying that this person is able to conduct the task that is they're told what they're supposed to have. So yeah, validation is really important. And then I really relate to your idea that you're proposing, by the way, on having these self-checkers. So having this always mindset of having a certain of beat, well, sometimes it's a redundancy, but also the algorithm checking for the model, checking itself all the time and assessing its performance, and also communicating it to the users in a calibrated manner, because that's also something that to be mindful of. It's also one of the ways to build up trust. And humans are actually pretty fastly adapting to technology, more than, and I think they jump to that faster than we hope for. Like if the car drives well on the highway, they can have more confidence on it than it actually is. And they believe, people can believe that it's more intelligent than it is, and I think there is the problem. I think less worried about the panicking, but more people rely too much on the competencies of the car. And when you couple it with some bad advertising and over whatever else, exaggerating its actual capability,
Thank you, Alexander. I think we are getting kicked out.
So maybe standard and specifications, and also consensus and the coordination between all the stakeholders, especially industrial stakeholders. So I think these are all important points.
Yeah, I think it's an incredible, difficult exercise to answer questions on the spot, and I think the panelists did an amazing job. So let's thank them for that.
Huge thank you to the organizers. So on behalf of speakers, I'm sure all of us here, on the whole thank you. Yeah. Awesome.
No. I think, yeah, that's all for today's workshop. Thank you all for attending our workshop. Yeah.